So, this is the tutorial 6. Here I will cover how you can fine tune some of the transformer. So, here I have covered in this tutorial on the BERT. So, what is BERT? So, BERT stands for bidirectional encoder representations, right? Just a minute. Yeah. Bidirectional encoder representation from transformers. So, which is released in 2018. This is very popular transformer. So, you already know the attention thing. So, here I will just cover the fine tuning. So, why fine tuning is important, you can go through this. So, for the disclaimer, I have taken this tutorial adapted from the Chris McCormick and Nick Ryan. Okay, this tutorial is adapted from there. So, in this tutorial we will use or you will fine tune BERT for text classification tasks. So, we will take some of the sample data set, we will try to classify the sentences. So, here you need some of the GPU instances for training, otherwise it will be very slow. So, those of you who already do not know how to change the CPU to GPU, you can simply do like this. So, I have for this tutorial I have taken the T4 GPU as some instances, right. Then first you have to check whether is GPU is available or not. So, I will show you two ways, one through the TensorFlow library, another through the PyTorch library, how you can check whether GPU is available or not. You can simply import TensorFlow as TF, then you can test the tf.test.gpu device name. So, if you run this cell, if there is some issue, it will show that GPU device not found. If there is some GPU, it will show. See, it is showing it has found GPU, only one GPU, which is GPU:0. If you want to check the same way through the torch library, you can simply call if torch.cuda is available or not. If so, then it will show you. See, there is one GPU available, we will use the GPU, and the GPU is the Tesla T4 GPU, which is free, you can take from the Colab, right. So, for this tutorial we need the transformer library, you can simply install by pip install transformers. And in this tutorial I have taken one data set called COLA data set, which is the corpus of linguistic acceptability. Okay. I will show some of the samples of the COLA data set and what is the particular task. By sentence classification, what I mean. So, this is like grammatical correct or grammatical wrong. So, you have to classify whether that sentence is grammatical correct or wrong. Now, here also I have shown how you can download and extract some of the data through some website, right. You need another package called wget. Okay. So, the data CG hosted in this GitHub repo, you can get there. So, let us say from this GitHub repo there is one zip file, I want to download that data set through wget package. What you can do? You can simply pass that URL to the wget library. Then you can call wget.download particular URL, then you can provide the path where you want to save that. Okay. Let me download it. Then once it gets downloaded, I have to unzip it, right. Okay. Now, I have unzipped it. So, those things you can get here. You see there is some temporary folder created Cola public, and you can get all of these contents here. So, this is temporary because after some time it will be lost. Okay. There is some session timeout, if it got done, then your all the variables, all the folders which I have created temporarily, that will be lost. Okay. So, I have to go first, then let me first parse those data sets. In order to parse, you can simply call the pandas package, pandas, then I am just reading that particular data set. So, here I am reading the train instances. So, as you can see, the number of training instances is 8551, and as you can see the label is 1 and 0. Okay. And 0 is unacceptable, which is grammatically incorrect, and 1 is acceptable, which is grammatical correct. So, for some sentence you can see there showed oil in price, okay, which is grammatically incorrect. For that reason we are getting the label as 0. So, this is the training instances, and some sentence which is grammatical correct, like Tom believes Stephen to be irritating, which is 1. So, this is the supervised task. So, BERT is already pretend on some other data set. We want to fine tune on a particular specific data set, and there might be many tasks. So, here I have chosen sentence classification task, and I want to fine tune on this particular specific data set called COLA data set, where I want to classify a sentence whether it is grammatical correct or not. If I want to see some of the only 5 samples, you can do like df.log, then you can get, see, the I kicked yourself, the man a ball kicked, which is grammatically incorrect. Yeah. Now, let us extract the sentences as labels of our training set as numpy arrays, right. Then what we have to do? We have to tokenize and format the input. So, from transformer, in order to tokenize, we are inputting the BERT tokenizer package. Okay. So, under BERT tokenizer, there are many pretend models, which is BERT base, uncased. There are many models you can check. So, if you want to check what are the models available, you can go to this BERT tokenizer thing, that class, then you can get what are the pretend thing you can choose. So, for this exercise, I have just taken BERT base uncased pretend library, pretend model. Then first I have to do the tokenization. How you can do? You can simply invoke the from pretend function from the BERT tokenizer library, BERT tokenizer dot pretend. Then you can specify what model you want to take as a tokenizer. So, it will take some time because the tokenizer will be downloaded, the config file will be downloaded. Now, it is got done. Okay. Now, let us say for a particular sentence I want to showcase what are the tokenized words. So, let us say this is the original sentence, our friends owned by this analysis, let alone the next one we propose. This is the original sentence. Then we have tokenized this sentence into some of the tokens. See, our friends owned. So, you can see owned has been tokenized into 2 token, one is WNN, another is T. By this analysis, let alone the next one we propose, right. So, here including the comma, full stop, everything will be tokenized. Then for each of the token, you will get some of the token IDs. So, how you can get? I have taken the first sentence, I have already taken the tokenizer, which is the BERT base uncased pretend model. Then I am just simply calling tokenizer dot tokenize. You can pass this sentence. Then if you want to take the, you want to check what are the token IDs, you can simply convert back those tokenizer to convert token to IDs. You have already got the tokens, you can convert into IDs. As you can see, there are different numbers, right. So, now our is being indexed with 2256, friends is 2894. These are the token IDs, because we will only work with numbers, right, not the actual words. Then there are some special tokens that you have to, like ACP, CLS. So, for the classification task, as you can see, there are 12 layers, and the first one is the CLS, which is a very specific token, and that we want to so the output, that is the 12 transformer layer, the first embedding, which is corresponding to the CLS token, that is being used for the classification task. Okay, that CLS one. So, this you can go through some of the theories. Now, let me tokenize these sentences all. So, first I have showcased how you can tokenize a single sentence, but we have in this corpus we have many sentences, like 8000 sentences, 8500. For each of the sentence I have to call that tokenizer. So, first we have to encode each of the sentence into the tokens, that you can do like tokenizer dot encode. Then you can pass that particular sentence. So, like that we have tokenized all of the sentences, and we are just calculating what is the maximum sentence length, because that is required. So, just in case there might be some longer test sequences for the design, for the training of this BERT fine tuning task, I am just setting the maximum length as 64, though we are getting only 47 maximum sentence length. Okay. But in the test, if you get some higher sequence length, you will get some error. So, this is the tokenization part where I have tokenized all of the sentences. Now, what we will do? See, these are the steps. Encode, what we will do? It will tokenize the sentence. It will prepend the CLS token to the start. So, for each of the sentences, it will append one special token called CLS, which will be used for the classification task, that is called CLS, and it will append another particular token called ACP, which is a separator at the end. So, first is CLS, then you have particular token IDs for that particular sentence, then you have the another particular special token called ACP. Then we have to map tokens to their IDs. We have to either pad or truncate the sentences to the maximum sequence length, right. Each of the sentence having the variable length. So, we have to either sometime we have to pad or sometime we have to truncate the sentence to the maximum sequence length. Then we have to create the attention mask for the pad tokens. Okay. Now, as you can see, tokenizer dot encode plus, it can tokenize all, it can do the all the stuffs. So, for a single sentence, we can see what are the attention mask and the token IDs. Yeah. So, this is the original sentence, right, and these are the token IDs. So, as you can see, the last one is getting zeros, right. Because this is for the padding. Now, we are randomly splitting this Scholar data set into some 90% training and the 10% validation set. Then from the torch.util.data, you can take the help of the tensor data set, which can combine the training inputs into some tensor data set. So, because you have to convert these input IDs into some of the tensor, then you can simply split this data set into 90% training and the 10% testing. So, we have I think total 8500 or something. So, we have converted splitted into that 7600 examples at the training data set and the 856 as the validation samples. Now, we have to create one data loader. So, under torch.utils.data, you have some package called data loader, that you can take the help just to, because each of the sentence now you have to batch, right, you have to create a data loader. So, the training samples is you can pass those train data set and you can simply specify some of the batch size, then you can create the data loader for the training and the validations as well. So, through the data loader package you can pass the train data set, you can specify what should be your batch size, then it will create the data loader for you. For any specific data set, if you follow this method, you can fine tune for any data set for any task, and these are the all the steps you have to follow. Then we want to train the classification model. So, for here we are just want to classify a sequence, right. There might be many tasks for fine tuning. One might be the BERT model for pre-training, BERT for masked language model. So, here I have taken BERT for sequence classification. There might be BERT for token classification, there might be question answering, something like that. But in this task I will cover only the sequence classification, because I want to classify each sentence into grammatical correct or grammatically wrong sentences. Now, because we want to work with BERT for sequence classification, so from the transformer we are importing that particular package BERT for sequence classifications. Along with that we need some other package AdamW and BERT config. So, here I am just defining. So, we have to take the some pretend model, right. On top of that we want to fine tune. So, I have already shown you that I have used the BERT base uncased as the tokenizer. So, that is the model which uses the 12 layer BERT models with an uncased vocabulary. You do not have any casing, lower casing or upper casing, and number of output labels you have to define. So, this is the classification task where we want to classify into 2 class. So, this is the number of labels as 2, right, and whether you want to return the model attention weights or you want to return the hidden states, that you can define by the output attentions or output hidden states by assigning true or false. Because you want to train this model in the CUDA, for that reason you have to take that model to CUDA, that you can simply tell the PyTorch to run this model to the GPU. You can simply call model.CUDA, right. So, it will take some time, because first I think this is 440 MB size model, which is BERT base uncased, which will download. you can see this is the whole model, right. You can see the embedding. So, here they have used, I have already told you in practice they use some higher dimensional embedding, right. As you can see, there is 30,522 is the vocabulary size which BERT based uncaged used, and 768 is your embedding dimensions. So, if you see the model, so this is BERT for sequence classification. We have taken BERT based uncaged model. The BERT embedding layer, this is the word embedding, this is the first embedding layer which having this dimension. So, this is the vocabulary cross embedding dimension. Then you can see there is some position embedding they have taken, there is some token time embeddings, layer norm, so on, and you have some encoder which is 12 layer, right, 12 BERT layer. So, you have like 12 blocks of attention, you can see the BERT attention, right. As you can see, I have already shown you some query, key and value, right. So, here also you can see some of the query which is the number of input cross output which is 768 cross 768, and key and value, right, all are 768 cross 768, and you have some intermediate and some output layer also, and in between you have some activation function and some of the pooler also, right. Now, get all of the model parameters as a list. Okay. Now, if you want to check, see, we have 201 different named parameters. So, for your simplicity, I have just printed all of the model parameters. Like in the embedding layer, you can see that you can call by BERT dot embeddings dot one embeddings dot weight. You can get that particular matrix or particular weights. If I want to check what was the initial weights for the position embeddings, you can get like this. You can get the token type embedding, you can get the layer norm, everything. And all of the layers, like first I have just printed here layer 0 only, but you can do BERT dot encoder dot layer dot 1 or 2 like that. And for each of the layer you can check what was the particular query weight, what was the bias, what was the weight for the key, what was the value for the value matrix, like that. And in the output layer also you can get what are the dimensions. Now, you already defined data loader, you have already converted your sentence into tokens, then tokens into some of the tensors, you are done. Now, you have to train this, you want to fine tune this on this task, because you already know for some of the sentences you already know what are the level, you want to leverage those supervised data. Now, you have to define some of the optimizer and some learning rate. So, here I have taken again Adam optimizer, I have taken some learning rate 2e minus 4. Okay. You can define this optimizer. So, this is some I have taken some linear schedule with warm up just for better training or better optimization. Then you can define the training loop. Okay. So, before going to the training loop, I have just defined some of the function just to calculate the accuracy of the prediction. This is simply accuracy calculation. Then I have just defined some function just to take what is the time it is taken, and I am just defining some of the seeds just for reproducibility. So, you can define some of the seed value, then if you define these values like random dot seeds, np dot and torch dot manual seed. So, for any deep learning project you are working on, you can follow this. So, you have to define some of the seeds, and those seeds for random library, those seeds should be already predefined for NumPy library, for torch library, then you can reproduce. Otherwise, every time you run you can get different results, because in the first tutorial I have already shown, if you define some of the linear layer, by default it will randomly assign some of the weights unless you predefined automatically. And if I want to regulate this random thing just to be coming every time same, you have to define the seed. Then here I am just measuring the total training time, I am just training the epoch, I think. Let me change the number of epochs, just a minute, otherwise it will take so much time. Yeah, epochs is 4, it is fine, 4 epochs, it is fine. So, I am to train it for 4 epochs. Okay. Then what you can do, you can simply call model dot train, right. So, once you call model dot train, then you can get the results for a particular sentence, what is the result you are getting, you can calculate the logit, then you can simply back propagate the loss just to minimize the loss. Then again you call optimizer dot steps, right. So, here I am just documenting what is the average running time like that. So, it will run for, it will take some time. It is training. So, as you can see in the right hand side, it is showing some of the time, what is the time got elapsed. So, while it is running, let me tell you. So, we are recording some of the statistics from this epoch. So, what is the epoch number, what is the average training loss till that epoch, what is the validation loss, what is the accuracy, what is the training time, what is the validation time, which are optional, but if you keep track that, or if you want to debug some of the code, let us say after each epoch your loss is becoming higher or it is not optimizing, what is not, you are not able to minimize, you can keep track those important statistics just to debug your code. Okay. And we are reporting the final accuracy for the validation run like that. Okay. So, the logits that I mentioned, you can get the loss and you can, the logits are the output values prior to the activation functions, right, before applying to the softmax. Yeah. As you can see, this is the average training loss it took after first epoch, 0.49 is the training loss, and training epoch took this much time. And after first epoch, when we are running the validation set, I think we have 756 or 856 validation examples, we are getting accuracy as 0.84, which is very good. We are able to classify the sentence whether grammatical correct or incorrect with 80% accuracy. And after each epoch, I think we are expecting the accuracy will be improved, right. And to calculate the accuracy, I have already predefined that accuracy functions. As you can see in the above, you can see the accuracy I have already calculated here, right, because you already know what is the ground truth level for those validation samples and what is the prediction you are getting, whether if you are getting correct. So, out of 100 how many you are getting correct. As you can see, batch 2 is also near to completion. I will wait for another 2 epochs. Then whatever the statistics during the training you have taken, you can visualize into some of the tables that I have shown in the next cell. Okay. So, for each of the epoch, what is the training loss, what is the validation loss, this will change most probably, and what is the training time, what is the validation time. Yeah, epoch 2 has got done. I think we are getting accuracy 0.85. So, previously you see the training loss was 0.49, validation loss was 0.39, accuracy was 0.84. After the second epoch, the loss got minimized, accuracy got increased, validation loss got decreased from 0.39 to we got 0.38. Okay. Epoch 3 is running. I think it will not take much time. Then what you can do, you can simply plot from with the help of Seaborn or Matplotlib package, you can simply draw the curve of the losses. So, which is your training loss, and which for the training data set, what was the, for each epoch what was the loss, and for the validation what was the loss, you can simply draw that. And you can then again you can perform that particular model, you can take as the test data set and you can evaluate on the test data set. Okay. I will cover those, just give me a few minutes just to check whether it got completed. Yeah, I think epoch 3 is near completion. Yeah. So, you can check average training loss got reduced to 0.1. Again we did not get much improvement in the accuracy, I think 0.85, because you have to run, I think for 10 epochs you will get very good result on this task maybe. So, for this purpose, for the sake of time, I have just taken only the 4 epochs. Okay. But just understand the idea. Okay. So, if you follow this tutorial, you can adapt this for any of the fine tuning tasks. Okay, for if you want to use BERT, if you want to use other library also, the process is almost similar. Okay, once it gets completed, we will view the summary of the trading process, like the statistics we already taken in the during the training, right. Yeah, I think we have completed 200 batches out of 241 batches. I think it will take another 4 to 5 seconds. Yeah, I think average training loss, yeah, we see we got some improvement in the accuracy. So, after 4th epoch we are getting 0.86 is the accuracy, which is good. Now, let me run just to see the statistics of the, yeah, you can get the training loss 0.49. It started with 0.49, then 0.29, then at last we got 0.13, right. Though validation loss towards epoch got increased, but if you increase the number of epochs, it will be stabilized. And you can see the validation accuracy, we started with 0.84. For next 2 epochs the accuracy did not improve, but after 4th epoch it got it to 0.86. If you run for more epochs, the accuracy will be improved for sure. Then you can simply plot the curve, right, training loss and the validation loss curve, as you can see. So, more the epoch, the validation loss is decreasing. Then you can read the particular test data set, because we are here, you can see we have some I think raw, yeah, I think you have some test data set. So, your model is trained, yeah, out of domain dev, this is the test data set. Now, we want to check the performance. So, number of test samples we had 516, right. Then your model is trained, you have to predict for each of the test sample, then you have to take the help of the data loader, that you can do by tensor data set. Then for each of the test sample you can convert into some of the input IDs through the tokenizer, right, as you can see, right. See, here also we are calling an encoder. So, we are taking each of the sentences of that particular test, that is the DF here is the test samples data frame. Then we are taking each of the sentence, we are passing through the tokenizer, we are converting into some of the input IDs. Then we are calculating the attention mask, then we are just passing the input ID and the corresponding attention mask to the trained model. Then you can evaluate on the test data set, like we are predicting for 516 samples, yeah. Then we got 354 out of 516 as the positive samples, right. So, one more last things, how you can save and load, right. So, you can create one temporary directory, let us say model save, then whatever model you have trained you can simply save by like save pretend. So, there is one package called model to save under transformer, I think model to save, sorry, you can save like save pretend function. Okay. Then you can save both the model and tokenizer like this, model to save dot save pretend, then it will be automatically saved. As you can see here, temporary I think model underscore save should be created, let me just refresh it. Yeah, you can see model underscore save is created, and you can see this is the config and the tokenizer config, and the particular model dot save tensor is created, which is the trained model. So, once you then you can download this model and you can use later also. Okay. Then how you can load this model? Yeah, you can simply like do model class dot from pretend, you can simply define the model class and from pretend. I will share this Colab notebook, you can go through it. Okay. Okay. So, here I want to end the tutorial 6. Okay. Thank you.